What if I told you that right now, as you watch this video, NASA engineers are designing a submarine not for Earth's oceans, but for an alien sea 1.2 billion kilometers away? A sea where the temperature drops to negative 179 degrees Celsius, where the liquid isn't water, but pure methane and ethane, where waves as tall as buildings crash against shorelines made of frozen water ice as hard as granite. This isn't science fiction. This is a real mission concept with a real budget and a real timeline. By the end of this video, you'll understand why NASA believes sending a submarine to Saturn's moon Titan could be humanity's best chance of finding extraterrestrial life, and why what we discover there might terrify us more than comfort us. Stay with me here. This gets absolutely wild. Let me paint this picture for you so you truly grasp how insane this mission is. NASA wants to launch a robotic submarine into space, fly it for 7 years across 1.2 billion kilometers of the solar system, plunge it through an atmosphere 4 times denser than Earth's, splash it down into a lake larger than Lake Superior, and then have it autonomously explore the depths of an alien ocean for months, while sending data back to Earth. Oh, and here's the kicker. The radio signals will take over 80 minutes to reach us one way. So this submarine can't be remote controlled. It has to think for itself, make its own decisions, navigate an environment no human has ever seen. The submarine will have to withstand pressures, temperatures, and chemical compositions that would destroy any vehicle we've ever built for Earth's oceans. And that's just Titan. NASA is also developing submarine concepts for Europa and Enceladus, moons of Jupiter and Saturn that hide liquid water oceans beneath miles of ice, oceans that might be teeming with microbial life. Or something far stranger. You might be thinking, why would we spend billions sending a submarine to another world when we haven't even explored most of our own oceans? That's exactly the right question, and the answer will fundamentally shift how you think about the search for life in our solar system. Okay, to truly appreciate why NASA is pursuing something this ambitious, you need to understand what makes Titan, Europa, and Enceladus so special. Let's start with the basics. For decades, scientists assumed that liquid water was essential for life. Our biology runs on water. Every living thing on Earth depends on it. So the search for extraterrestrial life became, essentially, a search for liquid water. The problem? Space is cold, very cold. Most bodies in our solar system are frozen solid. Any water that might have existed has long since turned to ice, or so we thought. This is where things get strange. In the 1990 seconds and 2000s, spacecraft like Galileo and Cassini began sending back data that rewrote our understanding of the outer solar system. Europa, one of Jupiter's largest moons, was hiding a secret. Beneath its icy surface, warmed by tidal forces from Jupiter's massive gravity, lies a global ocean of liquid saltwater. We're talking about an ocean that might contain twice as much water as all of Earth's oceans combined. Enceladus, a tiny moon of Saturn, was even more surprising. In 2005, Cassini discovered geysers of water vapor and ice particles shooting hundreds of kilometers into space from the moon's south pole. Something beneath the surface was generating enough heat to maintain liquid water and blast it into orbit. But Titan? Titan is in a category all by itself. Titan is the only moon in our solar system with a thick atmosphere, an atmosphere denser than Earth's, composed primarily of nitrogen with traces of methane and other organic compounds. When Cassini arrived in 2004, and deployed the Huygens probe, scientists got their first glimpse of Titan's surface. What they found was almost impossible to believe. Rivers, lakes, seas, an entire hydrological cycle, just like Earth. Except instead of water, Titan's cycle runs on liquid methane and ethane, hydrocarbons that are gases on Earth but flow as liquids in Titan's extreme cold. Kraken Mare, Titan's largest sea, covers an area of about 400,000 square kilometers. That's bigger than the Caspian Sea. Ligeia Mare, the second largest, is nearly as vast. For the first time, we had confirmed the existence of stable liquid bodies on another world besides Earth. And where there's liquid, there's chemistry. Where there's chemistry, there might be life. But here's the catch. Nobody has ever designed a vehicle to explore an ocean of liquid methane. Nobody has ever attempted to land anything in such extreme conditions. Nobody has ever tried to operate a submarine 1.2 billion kilometers from home with an 80-minute communication delay. Until now. NASA's Jet Propulsion Laboratory, the same team that built Curiosity and Perseverance, has been working on submarine concepts for over a decade. And what they've developed is unlike anything humanity has ever attempted. Now, what I'm about to reveal in the next few minutes will take you inside the actual engineering of these space submarines and the mind-bending challenges NASA is solving to make them work. If you're fascinated by cutting-edge space exploration and want to stay ahead of the biggest stories in science, you're in the right place. Hit subscribe and turn on notifications right now, because I cover missions like this every week, often before they hit mainstream news. What NASA has planned for the 2030 seconds and 2040 seconds will blow your mind. Let's get into the details. The story of NASA's space submarine begins not in a laboratory, but in a conference room filled with frustrated engineers asking an unusual question. What would it take to explore Titan's seas? The year was 2009. Cassini was still actively orbiting Saturn, sending back increasingly detailed images of Titan's hydrocarbon lakes. Dr. Ralph Lorenz, a planetary scientist at the Johns Hopkins Applied Physics Laboratory, was among those captivated by what he was seeing. Lorenz had spent years studying Titan's atmosphere and surface, but the lakes posed a unique opportunity. Unlike the surfaces of Mars or the Moon, which could be explored by rovers, Titan's seas required a completely different approach. You can't drive a rover across a lake. You need something that floats, something that dives, something that navigates. You need a submarine. In 2014, NASA's Innovative Advanced Concepts program, known as NIAC, funded the first serious study of a Titan submarine. The project was led by engineers at the Glenn Research Center in Ohio, working alongside Lorenz and other Titan experts. The challenge was immediate and overwhelming. First problem: temperature. Titan's seas sit at around -179 degrees Celsius. At those temperatures, most materials become brittle and electronics fail. Standard batteries don't work. Lubricants freeze solid. Seals crack and leak. Second problem: pressure. While Titan's seas aren't extremely deep, the submarine would need to withstand the crushing pressure of launch, the vacuum of space, atmospheric entry, and then immersion in liquid methane. That's an absurd range of conditions for any single vehicle. Third problem: communication. Radio signals from Titan take between 70 and 100 minutes to reach Earth, depending on orbital positions. The submarine can't wait for instructions. It has to be fully autonomous, capable of making complex decisions without human input. Fourth problem: power. Solar panels are useless on Titan. The sun appears as just a dim glow through the thick haze. The submarine would need a radioisotope thermoelectric generator, or RTG, similar to what powers Curiosity and Perseverance. But an RTG generates heat, and heat in a cryogenic liquid creates bubbles. Bubbles interfere with sonar, communication, and buoyancy. The engineering team spent years working through these challenges, publishing their findings in technical papers that read like science fiction. But here's where the story takes a turn. In 2017, the Cassini mission ended spectacularly, with the spacecraft deliberately plunging into Saturn's atmosphere to prevent any possibility of contaminating Titan or Enceladus with Earth microbes. With Cassini gone, direct data from Saturn's system stopped flowing. But the mission had left behind a treasure trove of information about Titan's seas, depth estimates, composition analyses, shoreline maps. Armed with this data, the submarine concept evolved rapidly. By 2020, a new NASA study had produced a detailed design for a Titan submarine capable of spending 90 days exploring Kraken Mare. The submarine would be about 6 meters long, roughly the size of a small recreational boat. It would carry cameras, sonar, chemical sampling equipment, and a suite of sensors designed to detect organic molecules. But the real breakthrough came in understanding Titan's methane. Unlike Earth's salty oceans, Titan's seas are remarkably uniform in composition. They're essentially pure hydrocarbon with minimal dissolved gases or suspended particles. This actually simplifies some aspects of submarine design while complicating others. The submarine could navigate using sonar optimized for methane rather than water. Its buoyancy could be precisely calculated without worrying about varying salinity. But the extreme cold and unusual chemistry meant that virtually every component had to be redesigned from scratch. By 2023, NASA had tested prototype components in liquid nitrogen baths, simulating Titan's temperatures. Motors worked, sensors functioned, communications systems transmitted. The submarine was no longer a fantasy. It was becoming reality. And then scientists started asking the really big question, what might we find down there? All right, let's talk about what the space submarines are actually designed to discover and why some scientists believe these missions could be the most significant in human history. There are 3 primary targets, each with its own submarine concept and its own potential for groundbreaking discoveries. Target number 1, Titan. The Titan submarine is designed to explore Kraken Mare, looking for something called prebiotic chemistry. This refers to the chemical processes that might lead to life but haven't yet produced living organisms. Here's why Titan is so fascinating from an astrobiology perspective. Titan's atmosphere is constantly bombarded by ultraviolet radiation and charged particles from Saturn's magnetosphere. This energy drives chemical reactions that produce complex organic molecules which rain down onto the surface and accumulate in the seas. In many ways, Titan resembles what scientists believe early Earth looked like billions of years ago, before life emerged. A primordial soup of organic chemicals, energy inputs, and liquid medium. If we can understand the chemistry happening in Titan's seas, we might gain insight into how life began on our own planet. But here's where it gets really interesting. Some researchers have proposed that Titan might host life that operates on completely different chemistry than Earth life. Instead of water-based biology, Titan life might use liquid methane as its solvent. Instead of oxygen respiration, it might breathe hydrogen and consume acetylene. This would be truly alien life, not just microbes similar to Earth bacteria found on another world, but organisms based on fundamentally different biochemistry. The Titan submarine would carry instruments designed to detect such exotic life forms, including sensors that can identify unusual chemical imbalances that might indicate biological activity. Target number 2, Europa. While the Titan submarine gets most of the attention, NASA is also developing submarine concepts for Europa, and that mission might actually happen first. Europa's subsurface ocean is very different from Titan's seas. It's liquid water, possibly salty, possibly containing organic compounds delivered by comets and asteroids over billions of years. The ocean is warmed by tidal heating from Jupiter's gravitational squeeze, which might also create hydrothermal vents on Europa's seafloor. On Earth, hydrothermal vents support entire ecosystems that thrive without sunlight, powered by chemical energy from the planet's interior. If similar vents exist on Europa, they could potentially support life. The challenge is access. Europa's ocean lies beneath an ice shell estimated to be 10 to 30 kilometers thick. Any submarine mission would first require a lander that could melt or drill through the ice, a process that might take months or even years. NASA's Jet Propulsion Laboratory has been developing concepts for cryobots that could melt through Europa's ice using nuclear-powered heating elements. Once through, a small submarine could be deployed to explore the ocean beneath. The Europa submarine would be smaller than the Titan version, optimized for a water environment, but capable of navigating in complete darkness using sonar and chemical sensors. What makes Europa particularly exciting is the possibility of finding life similar to Earth life, water-based, carbon-based, potentially recognizable under a microscope. If life exists independently on Europa, it would suggest that life is common in the universe, emerging wherever conditions allow. Target number 3, Enceladus. Enceladus might be the most promising target of all, and also the most accessible. Remember those geysers Cassini discovered? They're still erupting, constantly shooting material from the subsurface ocean into space. This means we don't necessarily need to drill through ice to sample Enceladus's ocean. We can fly through the plumes and collect material directly. NASA's proposed Enceladus Orbilander mission would do exactly that, orbiting the Moon and flying through the geysers to analyze their composition. But some scientists want to go further. A submarine mission to Enceladus would target the source of those plumes, potentially exploring the tiger stripes, the fractures in the ice where ocean water reaches the surface. The submarine might only need to penetrate a few kilometers of ice rather than tens of kilometers like on Europa. Cassini already detected complex organic molecules and molecular hydrogen in Enceladus's plumes. Hydrogen is particularly significant because it suggests active hydrothermal chemistry, exactly the kind of environment where life might thrive. The space submarines NASA is developing represent a fundamental shift in how we explore the solar system. We're moving from surface missions to subsurface exploration, from looking at worlds to diving into them. And what we find might change everything. But wait, just when you thought you understood NASA's space submarine program, there's a complication that's causing heated debate among scientists and engineers. The missions might be too dangerous, not for the submarines, but for the worlds themselves. It's called planetary protection, and it's one of the most controversial issues in space exploration. Here's the problem. Any spacecraft we send to another world inevitably carries hitchhikers, bacteria, fungi, and other microorganisms from Earth. Despite rigorous sterilization procedures, it's virtually impossible to eliminate every single microbe from a spacecraft. For missions to places like Mars, this is a concern, but a manageable one. Mars is cold, dry, and bathed in radiation. Most Earth microbes wouldn't survive, but Europa, Enceladus, and Titan are different. They have liquid environments, potential energy sources, and possibly habitable conditions. Earth microbes might not just survive there, they might thrive. Imagine this scenario. We send a submarine to Europa's ocean. The submarine carries a few hundred bacterial cells that survived sterilization. The bacteria find conditions suitable for growth. They multiply, they spread. Within years, Earth life has colonized Europa's ocean, potentially wiping out any native life that might have existed and making it impossible to ever know what was truly there before we arrived. This is called forward contamination, and some scientists believe it's a near certain outcome of submarine missions to ocean worlds. Some researchers have been particularly vocal about these concerns. They argue that we should not send life-detecting missions to potentially habitable worlds until we develop better sterilization technologies or better ways to distinguish Earth contaminants from native organisms. Others disagree. They point out that the challenge of exploring these worlds might require accepting some contamination risk. If we wait for perfect sterilization, we might wait forever. The science is too important. There's also a philosophical question lurking beneath this debate. If we do find life on Europa or Enceladus, how will we know it's not contamination? Earth life and any life in our solar system likely share common chemistry, since we're all made from the same primordial materials. A microbe found in Europa's ocean might look very similar to Earth bacteria, simply because the building blocks of life are universal. Some scientists have proposed requiring multiple independent detections, finding the same type of life in multiple locations before claiming discovery. Others suggest looking for isotopic signatures that would differ between Earth origin and native organisms. But here's where it gets even more complicated. What if the life we find on these worlds is related to Earth life? This is the panspermia hypothesis. The idea that life might spread between worlds through asteroid and comet impacts. Rocks ejected from early Earth could have carried microbes to other bodies in the solar system. Or, conversely, life on Earth might have originated elsewhere and arrived here on meteors. If we find bacteria on Europa that shares genetic similarities with Earth organisms, we'll face an incredible puzzle. Did we contaminate Europa? Did life spread naturally billions of years ago? Or did Europa life seed Earth originally? These questions might be unanswerable, which is why some researchers believe we should approach ocean world exploration with extreme caution. There's also a growing movement advocating for what's called planetary parks, treating potentially habitable worlds as protected wilderness areas that should remain uncontaminated for future generations to explore with better technology. The debate continues, and it might ultimately determine whether NASA's space submarines ever actually launch. Okay, I genuinely want to know what you think about this. Drop a comment right now telling me which position you support. Position A. We should proceed with submarine missions despite contamination risks. The scientific potential is too great to delay. Position B. We should wait for better sterilization technology before exploring ocean worlds. Protecting alien biospheres is more important than quick discoveries. Position C. We should focus on fly-through missions rather than landing or diving. Collect samples from plumes without risking contamination. I read every single comment on these videos, and honestly, some of the most insightful perspectives come from you, my viewers, scientists, engineers, philosophers, and curious minds from all walks of life. Your opinion on this matters. Let me know what you think. Beyond the immediate mission challenges, NASA's space submarine program connects to some of the biggest questions humanity has ever asked. Think about what successful exploration of these ocean worlds would mean. If we find life on Titan, Europa, or Enceladus, even simple microbial life, it would suggest that life is common in the universe. Our galaxy contains hundreds of billions of stars, most with planets. If life emerged independently multiple times in our own small solar system, it's likely emerging constantly throughout the cosmos. We wouldn't be alone. Statistically, we couldn't be. But the implications go deeper than just biology. Understanding life in different environments would transform our knowledge of biochemistry and potentially revolutionize medicine and technology. Organisms that thrive in liquid methane might use proteins and molecules we've never imagined. Life powered by hydrothermal vents might offer insights into energy generation. The possibilities are endless. There's also a profound philosophical dimension. For all of human history, Earth has been our only reference point for life. Every organism we've ever studied shares common ancestry. We don't know if our biology is typical or unusual, robust or fragile, universal or unique. Finding life elsewhere would give us perspective. It would show us what life fundamentally is versus what Earth life specifically is. It might reveal deep laws of biology that we can't see when we only have one example to study. And then there's the question of intelligent life. If simple life is common on ocean worlds, what does that suggest about complex life? About intelligence? About civilizations? Some scientists believe that simple life might be everywhere, but complex life might be rare. The evolutionary steps leading to multicellular organisms, brains, and technology might require conditions that are statistically uncommon. Others argue the opposite. If life can emerge and thrive in the harsh environments of ice-covered moons, it suggests that evolution is remarkably creative and adaptable. Given enough time, complex life might be inevitable. NASA's submarine missions won't answer all these questions, but they'll give us data points we desperately need. And there's one more dimension to consider: the engineering legacy. Building vehicles that can operate autonomously in alien oceans will push technology in directions we can barely imagine. The propulsion systems, navigation algorithms, communication protocols, and materials science developed for these missions will eventually filter down to Earth applications. Deep sea exploration, autonomous vehicles, extreme environment operations. The submarines exploring Titan's seas in 2050 might inspire the submarines exploring Earth's deep trenches in 2100. Science and engineering advance together. Each mission builds on the last, and the missions we're planning today will shape the technology of tomorrow. Here's the hopeful part of this story. Despite the challenges, the debates, and the decades-long timelines, NASA's space submarine program is genuinely moving forward. The Europa Clipper mission, launching soon, will conduct detailed reconnaissance of Europa's ice shell, identifying the best locations for future landing and submarine missions. The Dragonfly mission to Titan, scheduled to launch in the coming years, will deploy a drone-like rotorcraft to explore the Moon's surface, gathering data that will inform submarine mission planning. Enceladus mission concepts are advancing through NASA's study phases with increasing support from the scientific community. And in laboratories across the country, engineers are testing submarine components in cryogenic liquids, proving that the technology works. The path is long. The timeline stretches into the 2040s and beyond, but the work is happening. The science is progressing. The submarines are being designed. Within our lifetimes, we might watch as a vehicle built by human hands dives into an alien ocean and sends back images of a world no one has ever seen. That's not science fiction. That's science planning, and we get to witness it. But NASA's submarine program isn't the only ambitious ocean world mission in development. In upcoming videos, I'll cover the Europa Clipper mission and what it might reveal about that moon's habitability. I'll explore the Dragonfly rotorcraft and how it will fly through Titan's thick atmosphere, and I'll break down the latest discoveries about what Cassini found in its final flybys of Enceladus. If any of that sounds fascinating, subscribe right now and hit the notification bell. You won't want to miss what's coming. Thank you so much for watching this entire video. Your curiosity and support make this channel possible, and I'm genuinely grateful you're here. Here's my final thought for today. Somewhere in the outer solar system, seas of liquid methane lap against frozen shores. Oceans of salt water hide beneath miles of ice, and humanity is building the vehicles to explore them. We are, without exaggeration, preparing to become an interplanetary species of ocean explorers. That's extraordinary. Keep looking up. I'll see you in the next one.